Welcome to the CBSE MathSmith. Do you want to master real numbers? In today's lesson, we'll explore Euclid's division algorithm, the fundamental theorem of arithmetic, and the mystery of irrational numbers. By the end, you'll not only understand these concepts but also be able to solve tricky questions easily. Let's dive in. Real numbers include both rational and irrational numbers. Rational numbers, like 1 by 2 and minus 5 by 2, can be written as fractions, while irrational numbers, like root 2 and pi, can't be written as fractions. But what makes them special? Let's explore two fundamental concepts. Euclid's division algorithm, as the name suggests, has to do with divisibility of integers. Stated simply, it says any positive integer, a, can be divided by another positive integer, b, in such a way that it leaves a remainder, r, that is smaller than b. The fundamental theorem of arithmetic states that every composite number can be expressed as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. Let's take an example. Now, let's apply the fundamental theorem of arithmetic to factorize 18,360 into its prime factors. We start by dividing 18,360 by the smallest prime number, 2. Since 2295 is odd, we can't divide by 2 anymore. Instead, we move to the next smallest prime, 3. Next, we divide by 5, the next smallest prime. Finally, 17 is a prime number, so we stop here. Thus, the prime factorization of 18,360 is 2 cube into 3 cube into 5 into 17. This means 18,360 can be uniquely written as a product of prime numbers, following the fundamental theorem of arithmetic. Now, let's use this theorem to find the HCF and LCM of 6 and 20. 6 and 20 can be factorized as HCF is the product of the smallest power of each common prime factor in the numbers. LCM is the product of the greatest power of each prime factor involved in the numbers. Did you notice something? The product of HCF and LCM of two numbers is equal to the product of the two numbers. This formula always holds for two numbers. Now, let's prove an important result using prime factorization. Suppose p is a prime number, and it divides y square. We need to show that p must also divide y. To do this, we write y as a product of primes. When we square y, all prime factors appear twice. Since p divides y square, and factorization is unique, p must already be present in y. Thus, p divides y. This proof is the key to understanding why numbers like root 2, root 3, and root 5 are irrational. Some numbers, like root 2 and pi, cannot be written as fractions. They are called irrational numbers. Let's now prove that root 2 is irrational. We will prove that root 2 is irrational using a method called proof by contradiction. This means we will assume the opposite, that root 2 is rational, and then show that this leads to a contradiction, proving that our assumption was wrong. Since we are assuming that root 2 is a rational number, there exists two integers r and s, such that root 2 is equal to r by s, where r and s have a common factor greater than 1. But we only want to work with numbers that are coprime, that is, having no common factors except 1. So, let us divide r and s by their greatest common factor to get a new fraction, y by b, where y and b are now coprime. By dividing both r and s by their common factor, we obtain a fraction y by b, where y and b are coprime, meaning they have no common factors other than 1. Now, Let's square both sides. This equation tells us that y square is divisible by 2. But what does that mean? Since y square is divisible by 2, it follows from number theory that y itself must also be divisible by 2. So, let's write y is equal to 2 into c, where c is some integer. Now, substituting y is equal to 2 into c into our equation and dividing both sides by 2, we get. Now, b square is also divisible by 2, which means b itself must also be divisible by 2. We now have a problem. We originally assumed that a and b were coprime, meaning they have no common factors other than 1. But we just proved that both a and b are divisible by 2, meaning they have at least one common factor, 2. This is a contradiction, which means our assumption that root 2 is rational must be false. Since our assumption leads to a contradiction, we will be rejecting it. Therefore, root 2 is not rational, it is irrational. This proof technique is widely used in mathematics to show that other numbers like root 3, root 5, and many square roots of prime numbers are also irrational. To recap, in this video we covered Euclid's division algorithm, the fundamental theorem of arithmetic, and the mystery of irrational numbers. Thanks for watching. If you found this video helpful, please give it a like, share it with your friends, and don't forget to hit the subscribe button. Be sure to check out our other videos for more topics and detailed solutions to challenging problems. See you in the next video. Bye-bye.